All right, we're back. Excuse me. So we've just finished talking about the KL transform, and now the rest of what I want to talk about is really about JPEG compression. And what JPEG does is it puts together a bunch of these different tricks into one kind of very messy series of practical steps, and I don't expect you to memorize every little detail of the steps, but I want you to understand the basic ideas of them and what they're for. Now, I explained in the KL transform that the idea is to find a set of basis images such that the compression would work as well as possible. But that approach that I described for image compression wasn't so practical because it really relied on your knowing ahead of time the kinds of images you would have, because it had in it this matrix Rx which had statistics about the images, and you may not know that ahead of time. I mean, if you're trying to make an algorithm that would work for any images on the web, you don't know what people are going to be trying to store. So that approach, the idea of the approach was smart, but it's probably not practical the way I described it. So it has two disadvantages, practical drawbacks. One is that the basis vectors depended on this covariance or correlation matrix, which depended on the images that you would expect, as I just said. Another is that there's no fast KL transform algorithm the way there's a fast Fourier transform, FFT, or fast discrete cosine transform, which is the one we're about to learn. And so what we do is, or what the JPEG approach does, is to say, well, we want to try to do this KL transform idea, but we don't really know much about the images and their correlations between all the pixels. But we do know that images tend to have some kind of correlations in them. So let's imagine a simpler assumption. Let's just assume that if I have a picture, let's see, here's a picture, and I have, let's say these are two pixels next to each other in the picture. It's pretty safe to assume that those two pixels will tend to be correlated with each other. You know, you look at any two places on this piece of paper, and there's a good chance that the brightness of the two adjacent pixels is similar. It won't always be true, like if I have a pixel on here on the line and the next one is off the line, they'll be quite different. But by and large, it's not a bad assumption. So it's been shown that if the image is assumed to have statistics such that it's a Markov source of order 1, then the KL transform turns out to be a simpler thing. It's simply a transform that we can write down that looks a little bit like a discrete Fourier transform. Now this is just fancy language to mean that we assume that pixels that are immediate neighbors, that's what order 1 means, are correlated, but that other pixels that are farther apart are not assumed to be correlated. Now, in real life, there may be correlations among pixels that are very far apart, and this method doesn't capture that. But it's a very bland and simple assumption that's it turns out to be helpful. So if you make that assumption you can prove mathematically that that fancy KL method that I described produces as its basis vectors these cosine functions. And so the coordinates in that that representation we described would be computed by doing this transformation, which is called a discrete cosine transform, or DCT. That's a D. Okay, so it looks a lot like a DFT, right? We have our double sum of the image, and then we have something here with frequencies in it, K and L. But instead of e to the minus j type of thing, we have just a product of cosines. So it's a separable, these are separable functions. They're cosines. These are like stripes in the horizontal and vertical directions. And they look like this. So you should have handy for this lecture, I should have mentioned, the handout that's called JPEG handout. And, you know, I'll be referring to this one a lot, which was in an email. So these are the cosine functions I was talking about. Now this diagram's, I realize, a little bit misleading. Where it's blank here, there's really, these are really little images. Okay. All right. So they're little 8 by 8 pixel images. The reason for 8 by 8 will be clear when we get to the JPEG algorithm. The JPEG algorithm breaks the image down into little 8 by 8 pieces. Okay, so here are different ones of these cosine functions. This is where the spatial frequencies are 0 and 0. So that's DC, right? As you go this way, you're increasing the frequency for the horizontal direction, right? This is getting, you know, bright, dark, bright, dark. And then if you go down this way, you see you're getting to high frequencies in the vertical direction. And then as you go this way, you're increasing both the horizontal and vertical. So these are the basis functions, basis images, basis vectors, I guess you could say, that are describing what's happening in the DCT. What we're saying is that any image, which is, let's say, 8 by 8 pixels, can be made by adding these little images together in the appropriate amounts. And the amounts are the transform coefficients. So it's just like you would do in a DFT. Same idea. It's just that the functions you're adding together are different. They're these cosine functions. So here they are. And as we saw in this example, when you add them together in the right amounts, going to higher and higher frequencies being added in, you eventually will get this letter A. JPEG will use this idea, similar to what we talked about with the KL transform. Will basically not convey all this high frequency stuff necessarily, and use that as a trick to save space, to compress the file. Okay, so that's the discrete cosine transform. These are the transform coefficients, and these are what we need to multiply those little cosine images together. To multiply the cosine images by, so that when we sum them up, we'll get the image back. These are just some facts about it. Now, the The JPEG algorithm is messy. It's just a whole series of little steps that people came up with that tries to use various redundancy ideas to keep squashing down the size of the files. JPEG stands for this. This is the name of a committee that decided on this standard method. So we all agree on how JPEG works, so that if we receive or send a JPEG file, we all understand what it means and how to read the file and how to use the file. So the first step is, so this represents an image. Could be a very large image. I've drawn it to be not a very large image. JPEG starts by breaking the image into little 8x8 pixel boxes, little tiles called blocks. And it then, most of the time is spent, most of the steps involved in the compression involve taking that each little 8x8 square and representing it with a very small number of bits. So this figure, this page of the handout, from the JPEG handout, describes a bunch of the steps. I think it might be useful to kind of review the steps once real quickly, so you see where we're headed, and then I'll back up and we'll look at each step more carefully. So what we have here is an example of a little 8x8 block that we imagine is just a piece of some real big image. So let's say that I have some, I have this fancy digital camera, might have 20 megapixels, 20 million pixels in it, but I'm still going to break it into little 8x8 tiles. And then one at a time, I'm going to take the numbers, the pixel values, so these are the pixel values in a little 8x8 region, and I'm going to re-represent them with a very fancy code which will capture most of the interesting and important things about the image in a way that makes a very small file. This is a particularly nice example because there's a lot of redundancy here, right? Remember, way at the beginning I introduced a very simplified example where I said, what if you had an image where every pixel had a value of 100? Well, then obviously I don't want to repeat 100, 100, 100. It's redundant. Similarly here, most of the values are around 150, 160, something like that. So there's clearly quite a lot of redundancy here, and I should be able to store this more efficiently. So so let's sort of quickly run through the steps and then back up. So the first step is you take the discrete cosine transform of this to get this. So this is the capital F. On my notes, I guess this is called KL. This is MN, but the idea is the same. Okay. So each of these is a frequency component. Each of these numbers corresponds to these functions. So what this means is, if I want to create that image, I should take a little uniform image and multiply it by 1260, and then take this image and multiply it by -1 and add those together, So that's my summation in the transform. And I do that for every element of this array is telling me how much of these guys I need to add to create that. And this is an invertible transform, just like a Fourier transform. So if I do that, I'll get exactly this image. Okay, so no loss of information if that was all there was to it. Now, the DCT, if you look at the values here, has done something kind of magical because of what we learned about the motivation from the KL transform. Remember the KL transform, let me see if I can find the diagram from that earlier lecture. Remember what the KL transform did. Now remember, there I was using height and weight instead of pixel values, but imagine these are two different pixels, and if they tend to have the information spread evenly between the two pixels, what the KL transform will do is to move the information so that it's mainly in one of the two coefficients of the transform. So in the original representation they were kind of spread out. These are the same. In this representation the information is bunched up in the first one. Well, we can see here that the DCT did the same thing. You see how all of these are quite uniform. But now that's not the case. It's taken the information and it's pushed it kind of toward the upper left corner here. So the DC now is a huge number. And the rest are very, very small numbers. So even if we didn't do anything else, this has done a kind of compression, because you see these are, to represent each of these numbers, it takes a lot of bits. This number takes a lot of bits, but all the rest of them are very tiny numbers, and we can see intuitively that you should be able to represent them with a smaller number of bits. So that's the first step. The next step is complicated, so I'm going to kind of, in this first pass, I'm going to kind of skip the details. But what we do is we take this now compressed thing with the DCT. So this is our simpler representation than that. And what we're going to do is we're going to do two things at once. One is we'd like to store smaller numbers if we can, rather than bigger numbers. So we're going to divide all these numbers by something. And these are the things we're going to divide by. So we're going to divide this array by this array. And the other thing we're going to do is, after we do the dividing, we're going to round off the results. So if I take this array and divide by this array, and then round it to the nearest integer, I get this. And you see what's happened is everything in this area is now zeros. And that's because after we did the dividing, when we rounded off, it was less than a half, and so it rounded to 0. So we'll understand when we get into the details why that was a good thing to do, but let's just kind of appreciate the compression going on. We started with 64 numbers that were fairly big, so these were pixel values that we'd have to store. We now figured out we could store the same exact amount of information in terms of transform coefficients. If I just use all of these, I can exactly do an inverse transform to get that back, but this is nicer, right? Now what we've done is we've made the numbers smaller, and we've actually eliminated a lot of them. The eliminating process, what we've really done here is to discard high frequencies. Remember, these are frequency components. They're these the coefficients that you would apply to these high frequency cosines. And coming back to this diagram, which shows how it gets used, if I don't use these, right, then what I would have is an image that looks like that. It's pretty good, right? It's very important to use these low frequency ones because they define the shape of the letter A. You see, if I keep these low ones, I'm starting to be able to see this as an A. The high frequency ones make it look nicer and sharper, but if I just want to see what it is, they're less critical. And so on the web, the images you see typically are actually quite poor quality because it's understood that in that application it's not important. You know, it's the images are really small. You're only, you know, reading a newspaper or something, looking at a website or whatever, so it's not so critical. So it's these high frequencies that go. So that's represented by getting these zeros up here. Okay, so we've gone from a bunch of 64 pretty big numbers to, look, just a handful of very small numbers. Well, one not so small, but we'll come back to that one. The next step is we need to arrange these into a file, a computer file. Well, computer files are not two-dimensional. They're just a list of bits, a string of bits. So what we do here is, recognizing the idea that the low frequencies are the most important, we start reading them out into a list in this zigzag order. So we start from low frequency going towards high frequency, but we do it in this kind of snaking way. Then, once we've done that, I'm going to skip ahead in my notes just a bit, just to show you so that you'll see where we're heading. If I take these numbers and I read them out in the order that I just described, like this, here they are. There's the 79. I'll fold this so that we can see them at the same time. 79, 0, minus 2, minus 1, minus 1, minus 1. You see? That's how I'm getting these. And here's a source of compression. After I reach the last one that's not 0, all the rest are 0. And there's no use saving all those zeros. So instead, I put a marker. It says end of block. That means that's the end of communicating this entire block. So that's now the entire representation of this little piece of the image. That whole thing has been compressed to this list of numbers. But then I don't stop there. I use the prediction idea from the DPCM method from a previous lecture. This is a pretty big number, so I'd really like to get rid of that. So what I do is I assume that whoever's going to decode the image, the JPEG file, could use a guessing scheme, could guess that this DC value of a certain block of the image, they could guess that it's the same as the DC value of the previous block. So let's say here's the block I'm working on, the one we've been looking at, and let's say it has 79 as the value in the upper left corner. I could assume that, pardon me, let's say the previous one, the one next to it, was 78. I could, when decoding, guess that this one is also 78, and I'd be very close. So what the encoder needs to do is simply to alert me that if I try to do it that way, I'll be wrong by 1. So the encoder simply needs to tell me the value 1 so that I can correct my small mistake. And then the coder doesn't need to write 79. They just need to write 1, which is the difference between the 78 and the 79. Okay, so we went from this to this. We then did this quantize step, which gave us this. We read it out into a series of numbers. We then attacked this one using that other trick from before. And then, I'm going to skip here for a moment and we're going to come back to this. I then okay, so here's my series of numbers that now represents that whole block of pixels. And for each one, I'm going to use a kind of very messy coding scheme that's based on the Huffman coding. I don't expect you to memorize this particular kind of coding, only to understand. I want you to understand Huffman coding and how to make your own. But here it's a messy coding scheme. But what we're going to do is we're going to take each number here and represent it with a series of bits. You see, I'm putting a slash here so that we can tell which one is which. But here's my 79, and so on. Okay. So let's see. Let me get my notes in order again. Then this, we use that predictive coding approach to turn it into a code. And so in the end, this series of bits represents this guy. So this is just 30 bits. Makes a very good representation of all that stuff. All right. So that was the quick version. Now, because I don't expect you to really know every little detail of this, I'm not gonna, as we come back through it a little more carefully, I'm not gonna go too detailed about it, but let's just dig a little bit deeper. Oh, we've already talked about that. Okay. So the steps were, and now starting back at the beginning, we make 8x8 blocks. Here's one of them. We take the DCT, discrete cosine transform. That's this. This is an important step that's a bit tricky. This takes this guy, the DCT, and reduces it down to this guy, which looks kind of similar, right? It's a big value here, smaller numbers there, big one here, smaller here. And the way we get from here to here is we divide this DCT array by this array, which is called the quantization table. Now this is something that's pre-designed, and it can be stored inside the JPEG file so that the decoder knows what to do. There are also standard quantization tables. But this is a predefined thing. And what it's doing is two things. I'm not sure if I said it correctly, so let me repeat. So the way you get from here to here is you take this array, divide it by that array, divide each element, and then round it up to the nearest integer. So that does two things. One is it makes all these numbers smaller because we're dividing these guys by modestly big numbers. And then when we round them, we actually end up killing all of these guys. So we end up with a lot of zeros. So what effectively is happening is similar to what happened in that KL transform. We're throwing away dimensions or coordinates, thinking back to that description, that are less important. So remember in our height weight example, we concluded that size coordinate was a more important coordinate than the proportions coordinate, and that if we threw away the proportions coordinate, we still could get a good representation of the height weight pair with one number instead of two numbers. Same idea here. Instead of having all 64 numbers, we're going to have a few numbers that are going to capture most of the information. In the notes, and I guess you can go through them for yourself, basically what's happening here is I'm just giving a little example. I'm looking in detail at a few of the values in the table to see how they work. So I'm going to look at this one, and this one, and this one. Okay. So this is 0, 0, 1, 1, and 2, 2. So we just want to see what happens to them when we apply this idea. So the idea is as I said, you divide the DCT by the quantization table. I'm sorry, I'm at home and you hear people talking in the background. You divide these and then round it off. So when we divide 1260 by 16 and then round it off, we get a smaller number, obviously. And because the quantization table value is pretty small compared to 1260, when we do this rounding, the rounding doesn't do much. 1260 over 16 is this. If we round it, we get that, and that's almost the same. So the quantization table, whoever designed this one, was meaning that when we would do this step, we wouldn't change, the rounding wouldn't change the outcome very much. Now remember what's happening here is we're doing a series of steps that are encoding. We're making a code. After it's done, whoever gets this image file from us needs to undo all these steps to get back to the full image. If what we did here was to just take this and divide by this and then put that in the file, that result in the file, then we could undo by simply taking what's in the file and multiplying by that, and we would get this back, and it would be perfect. It's not quite what we do. We have this rounding. We round off each ratio, and so there we lose a little bit of information. And so this is the key thing I want you to know, is this quantization step, this rounding, is what makes JPEG lossy. Remember from the beginning, we defined lossy means when you uncompress, you don't get what you started from. So this was designed so that the DC is very accurately represented. You don't lose much. 79, 78.75, it's almost the same. So we skip as another example just to the, look at what happens to the 1, 1 element. This is frequency 1, 1. You take this, you divide by the corresponding Q, 17/12, minus 17/12. That's this. Well, now you can see, because 12 is close to 17, this rounding creates a large error. This is a much bigger relative error than what we had here. So this quantization table was designed in such a way to say, you know what, we better get the DC really close to being correct. And why is that? Well, because the DC is saying generally how bright is that little 8 by 8 square is the baseline. Remember, the DC is just a uniform thing. So we want to get that right, because if we don't, when we paste these little 8 by 8 tiles back together, we'll see the edges if they don't, if the brightnesses don't line up. But what we're saying is, well, when we get to a little bit higher frequency, it's okay. It doesn't have to be so perfect. So we'll allow this bigger error. And now let's look at what happens to the 2, 2 element. That's this guy. Well, you take this one and you divide it by this one. Minus 2/16. And then you round it to the nearest integer. Well, nearest integer of minus 1/8 is 0. So it's saying that this one, we're going to eliminate it completely. We're saying, you know what, it's not important enough to even bother saving that piece of information at all. Okay, so that's the procedure that takes us from this DCT to this kind of quantized DCT. So that's what we started with. This pushed the information toward the corner, and then this step just basically chopped off all this stuff and then shrunk the remaining numbers and rounded off the fractional residuals. Okay, all right. So then we're just going back through the second pass of explanation. We've explained this before. You now read these out in the zigzag order. And now you just get a list of numbers. And then you have a statement, a code that says that's the end. The rest are all 0. And then we use this idea that the block's DC coefficient can be predicted from the previous one, and that only the difference, the error, needs to be saved. Okay? So that's a way of knocking down this one remaining large number. This part, in previous years I spent a good amount of time explaining this, but I realized that it's kind of not very enlightening. It's just a lot of very specific details that were invented to create the specific JPEG algorithm. I don't think there's a great lesson, too many great lessons to be learned, but let me just try to quickly give you a feeling for it. I don't expect you to, memorize all the little details of this, but basically, after we've tackled the DC coefficient, so the 0, 0 one, we have all the others now to deal with. Those are called the AC coefficients. That just means all the other ones. And this uses a couple of ideas which I guess are worth getting a sense of. One is that we don't save the actual zeros that appear. Okay. So for example, I'm sorry, that's not the best place to look. All right. So after we've read the numbers out in zigzag order, we have that one big DC one that we've talked about. Then here are all the AC ones. Well, here you see we have a couple zeros in a row. And it's very common for there to be a group of zeros appearing. And we would prefer not to have to say 0, 0. We can just combine that statement. The way we do it is when we list out the number -1, part of the code is before the -1, put in 2 zeros. Okay, so there's a code that describes what's called the run length or zero run. That simply means how many zeros were there in a row just before the one that we're doing. Okay, the other idea that is used is along the lines of variable length coding, is that, as we see here, it's very common to have small numbers here, like -1. Not so common to have a bigger number like -2. And in our example, there weren't any numbers even bigger than that. So from variable length coding, we know that common things like -1, 1 should be stated using a short code, whereas uncommon things have longer codes. So the AC coefficients are categorized in JPEG. So this category 1 means small, 2 means a little bigger, 3 is still bigger, and so on. And then just plain old binary counting is used to say which one in the category is it. So in category 1, the number 1 is the 1th. I don't know how to say that. It has the number 1 to describe its place in this list. Okay, so again, don't worry about some of the details of this. I just wanted you to get a feeling for what goes into it. Okay, so in the end, to represent each number, there's a code word for the category and the run length, meaning how many zeros preceded the number, and then a code word to say which number is it in the category. And here's our example. So these are all the non-zero AC coefficients. This is how many zeros preceded each one. There's one with the 2 zeros. That's the category of these values. And then these are the code words. And these are taken from this code book, code table. This is a Huffman code. Now, obviously, I don't expect you to memorize this or even to try to generate it. This is not even all of it. But this is made in the same way as the very simple ones that Professor Bronkoff showed you how to do in the lecture that he covered. So basically, it's just the idea is you use the short codes for things that are very common and the long codes for things that are very uncommon. And if we string all of these together, this code represents all the AC parts. The DC part at this point is still this number 79 that we don't like. It's too big. So what we do is we use this prediction idea. And what we do is we look at the DC coefficient of the preceding block, the tile in the image just before the one we're looking at, and we use its value to predict the current one, and then use this number to correct the mistake. So knowing that this is what the decoder will do, the encoder figures out what the mistake is and then only saves the mistake, the error, in the file. The decoder uses the guessing. So for here, for this one, the decoder will guess 78, that this should be 78. He'll be wrong. He'll read out of the file the number 1 and add it, and he'll get his 79, which is correct. So the file doesn't need to save all these big numbers. These are some DC coefficients of blocks. They only need to save the differences, those errors, which are small numbers. So using the Huffman coding of these numbers, this fills in the very last piece of our code for this 8x8 block. So it's really cool. You start with this sea of very large numbers. There's 64 big numbers here, lots of bits, and that binary string describes the whole thing. Not perfectly, because of that one lossy step. Let's see how we did exactly. We started with 8x8 pixels. If each pixel was 8 bits, so that's 256 gray levels, it would take 512 bits to store that thing. In our little code, it only took 30 bits. And that makes a compression ratio of 17:1, so it's quite good. And that was so high in part because this was so uniform. If there was a lot more stuff going on in there, a lot of more interesting details to it, it wouldn't have worked as well. Okay, so let's just quickly summarize the outline of the algorithm. So you have the step of creating the JPEG file, turning images in the form of 8x8 blocks into a string of bits, and then you have the process of decoding, reading the file out, reading out the bits, and turning it back into an image that you can view. Well, creating the 8x8 blocks and then tiling them together and displaying them. So remember, it was DCT, divide by the quantization table, and round. I guess I should say, and int. This is the lossy step, remember. This is the lossy step. When you round a number, a ratio, and you lose the remainder, you can't get that back. Then the DC frequency is coded with this predictive coding, and then Huffman coded. The AC are Huffman coded, and then you have a series of bits. So what happened here? This used spatial redundancy, right? The DCT used the fact that the pixels in the block were correlated with each other. This kind of worked together with this and determined that because we had used this technique, that we had already compressed the important information up into the upper left corner of the array, and so we could throw away a lot of stuff. So this is sort of in line with the KL transform concept, right? This is again a spatial redundancy trick. This is within the block. This is between blocks. This was saying the pixels in a block were correlated with each other. This one was using the fact that the average brightness of two neighboring blocks tends to be similar. If I have two pieces of the image next to each other, if I would average the pixels in here and average the pixels in there, I would tend to get similar value. So that's spatial redundancy. And then here we hit it with a trick that takes advantage of coding redundancy. Okay, so we're using some of these different tricks that we've learned along the way. And in all of that, the only thing here that was not reversible is that rounding. If not for the rounding, I could take the bits and go back all the way through these steps and get back to perfectly to here. So in fact, it's possible to store a JPEG file in the JPEG format and have no loss at all. So JPEG isn't necessarily lossy, but it's usually used that way. But even if it's not lossy, you're still going to compress because this guy is being smart, this is being smart, and that's being smart. Okay, so that's coding. Decoding is we read the bits out of the file, we decode them with the Huffman table. The first word is the DC, and we use that predictive coding thing to unpack it. All the others go on forward. It all gets multiplied by the quantization table. So this is, here we divided, right? To undo it, we multiply. But because this had a rounding, we can't magically see through the rounding procedure. So when we do this multiplying, we don't get back what went into that. But it's close. Then we inverse the DCT, IDCT, and that gets us our block. Okay. So that's JPEG. The very last thing for the entire course is MPEG, and MPEG is really, again, a lot of messy details, and I think at this point, you're really not going to memorize all these anyway. What I'd like to just do is give you the flavor of it so you understand the concept, and you can read this at your leisure. I'm not going to hold you to the specific steps, but I would like you to understand the general concept that's being used. Okay, so MPEG stands for a different committee, moving picture experts groups. So this is for movies. So this is a way of compressing videos. JPEG used spatial redundancy and coding redundancy. Because we have movies here, now we can also use temporal redundancy. So from one frame of the video to another, there may be very little change or very simple changes, and so we don't have to communicate every frame of the movie. We can do the first frame, and then if the second frame is very similar, we can just describe the things that have changed. So it's about how do you cleverly communicate what changes have taken place. So one of the biggest ingredients of this is a big ingredient of change in a movie is motion. Things move around. Okay, so let's say, imagine a really simple scene where I have a sailboat that at the beginning is here, but over time, here's the next frame of the movie, and then the next frame of the movie. Over time, the boat is moving from left to right. It started out over here, but then it moves eventually to here. Right? Here, here, and there. Well, forget about MPEG for a second. If I really knew that the image was that simple, I could just send you a picture of the boat, and then in every frame I could tell you where to move it to. I could send you the picture and then say, okay, take the picture, and in this frame paste it here, and in this frame paste it there. And so for the first one I would have to tell you the whole image, but for the others I would simply tell you some XY coordinates, some spatial coordinates of how to move the boat around. And that's obviously much smaller than a lot of pixel values. It's just two numbers. So that's the essential trick of MPEG compression. And it's wrapped around the idea of motion estimation. The basic quantity in motion estimation is the motion vector. Motion vector is a vector describing the changes in spatial coordinates x, y from one frame to another. So if the boat was here and then it moves to there, this is the motion. This vector here is the motion vector. Okay, now I was trying to give you an intuition, so I made it sound really simple. You know, I have a boat, it moves around, I just tell you X, Y. Well, real videos are not so simple, right? Because even if I would have very simple motion, you can see that there are other changes happening. So let's say here's one frame of a movie, and then here's the next frame of the movie. Sorry, I'm messing up the focus there. But between the two frames, maybe my hand didn't change much. It's just a simple shift. But when my hand is here, this stuff's covered up. And then when my hand is here, this stuff is revealed. So there's not just the change of my hand, but there's the change of what was behind my hand. And that needs to be communicated, right? So MPEG doesn't take such a fancy approach where it tries to work out, oh, here's a hand, oh, here's where the hand moved. It's not as fancy as that. It takes a much simpler approach. What it does is, a little like JPEG, it breaks the image up, so there's an image frame, into a bunch of tiles. But the tiles this time are 16 by 16 pixels. And the tiles in MPEG are called macro blocks, or MB. So this is not megabytes, it's macro blocks. And what it does is it assumes that if there's a tile here in this frame, that there's a good chance that that piece of picture, that little picture, appeared somewhere in the previous frame. So imagine, let's say that my fingernail was 16 by 16 pixels, and that my hand moves. Okay, so from one frame to another, you could try to take this little part and see, was it over here somewhere previously? And it does that for each block. Now, I made it simple. I made it seem like, oh yeah, it just so happens that my fingernail exactly fits a square. Well, in real life, of course, these squares will, the boundaries of these squares will cut across real objects. I mean, my finger could very well, look like this in the picture, right? Could be in all parts of it appearing in many different blocks. So it's not that intelligent, but it can look at a piece and say, well, have I seen that piece before somewhere? To the extent it can track things and that the changes are motion, the idea of it, the way the compression happens is you predict between frames, just like we predicted in the DPCM method, and we use that in the JPEG to predict the coefficients, the DC coefficients. You try to predict where, so if I know the pieces here and I know the motion vectors, I can predict from this frame to another by moving little box-shaped areas around like a jigsaw puzzle and then putting them here. And then when it doesn't quite look right, that's okay, because the encoder and decoder both understand what prediction is being done, and what they'll do is the coder will record the error that takes place, and then the decoder will will read the error out of the file and use it to fix the mistakes. So what ends up getting transmitted are an image frame, motion vectors, and then the prediction error needed to correct the mistakes when these are used for prediction. The image frames are themselves compressed using JPEG coding, okay, because they're just images. So you can, all this stuff we're talking about uses temporal redundancy, but to get the one image frame, you got your Huffman coding, so your coding redundancy, and then your DCT gives you your spatial redundancy, and of course your DPCM and the JPEG as well. Okay, so what's on the remaining pages are little minute details about how MPEG specifically works, and I think I'm not going to bother to go through all these. You can read it if you think it's interesting. I really wanted you to understand this basic idea that it's patching together these blocks using prediction and then correcting the mistakes. This one ties together the whole algorithm, and again, I won't explain every detail of it, but essentially what it does is it says here's 9 consecutive frames, 0 through 8, and it treats them as a group called a group of pictures, and then the certain ones of these frames are actually transmitted full out, just the complete frame, pardon me, and then others are predicted from the ones that are transmitted, and then the errors are used to correct the mistakes. And the theory of this is that in most videos, things change eventually, so that in a 5-minute video, by the end of the 5 minutes, there's nothing showing on the screen that was there way at the beginning. So there's no use trying to predict that far ahead. So you just try to predict over very short time periods within the movie. Okay, so that is the very last page of notes for the semester. It was a lot of fun teaching you guys. It was a really good group this semester. I was really enjoying it, and I'm sorry I got sick on you, but we managed to finish to the very end. And I hope you got something out of it, and I look forward to seeing you in future classes.